Now I'm going to talk about Newton's method. If you recall, gradient descent method uses slope, which is first derivative. And Newton's method uses both slope, which is first derivative, and also a second derivative. So let me explain this using an example. Now, our goal is to find out this x-opt value, which makes this function minimal. Consider using the gradient descent method for this problem. And let's say we start from here. As you can see, the slope here at this point and slope at this point are not much different. The difference between these two values is very small. And that small value is represented by this small second derivative. So second derivative is small when the first derivative does not change much. In contrast, if we look at this part, slope is this, and the slope here is something like this. The slope 1 and slope 2 are quite different. So slope is changing rapidly. If the slope is changing rapidly, our second derivative becomes large. If you remember, we talked about this step size mu. And when slope is changing rapidly, our target might be very close. So if you are here, the slope is changing not much. And here you might want to have a larger step size or larger steps. Because slope is not changing, it means that probably your target is not close. So you want to move fast. But once your slope is changing fast, it may mean that your target is close. So your step size should be small. In other words, we want to have a flexible step size which reflects this second derivative. In other words, if a second derivative is small, then we want to have a large step size. And if a second derivative is large, then we want to have a small step size. This to have inverse relationship. So let me write down the gradient descent method here. Now, instead of having a mu, we can have something like some constant, let's say c, over second derivative at x-opt of n. So this is just a positive real number or positive constant. And in the denominator, we have the second derivative. So what does this mean? This means that if this derivative value is small, which means that the slope is not changing fast, then our step size, because this value is in the denominator, our step size will be large. On the other hand, if this second derivative is large, then we have large number in the denominator. So the whole thing becomes small, which in other words, if the slope is changing fast, just like here, then our step size becomes very small. And this is Newton's method.